This one is about load balancing and the way we are implementing it inside your routers. By the end of this video, and if I've done my job correctly, hopefully I'll answer to two key questions. What are the different load balancing techniques available in modern routing devices, and where it is the most appropriate to use one or another? Initially, I wanted to talk about technology only, but load balancing is very hardware dependent. That's why, to provide illustrations to the various points of this presentation, I will refer to Juniper products available in 2026. But don't get me wrong, you will find more or less the same concepts and ideas all around the industry. Okay, let's start with some basic concepts and definitions. The job of a router is to route packets. Yeah. Okay, the router routes packets, and to make this decision, it will rely on a FIB table, forwarding information base, itself derived from a RIB table, routing information base. These tables have been created based on the reachability information advertised by the other routers in the network or the internet, using routing protocols. I told you I will start with basics. Now imagine you have multiple options to reach a specific destination. The job of the routing protocols will be to compare their respective costs or metrics and to pick the best ones. If more than one of these options happen to have the same metric, that's an equal cost multipath scenario. And at this point, we can decide to program these multiple entries in the RIB table. After computation of the next hops and encapsulations, these entries are programmed in hardware in the FIB of the forwarding ASIC. One quick note here, I will alternate between PFE, for Packet Forwarding Engine, NPU, Network Processing Unit, Forwarding ASIC, chipset, etc. I refer to the same component here. It's just to limit the number of repetitions. So let's continue with our scenario. We have a packet targeting for this particular destination, the one with multiple paths and next stops. This packet is received on an interface of our router. It will be handled by the ingress NPU. The lookup phase will reply with a specific object made of multiple entries. But the packet can just use one path, right? So we need a local mechanism to decide which egress interface should be selected for the forwarding decision. And ideally, this mechanism should be smart enough to optimize the distribution of the packets and the load on the different links. We want to avoid unbalanced links utilization, or even worse, we want to avoid a congestion on one link if you have free bandwidth on the others. You understand that our multipath destination can be one hop away, and in that case, the scenario will be very much like a link aggregation use case. Or it could be resolved through a succession of routers that will be translated in our software and hardware into a hierarchy of next hops. But again, I insist on this particular point. It's a local process. When the packet is sent to the next router, it starts again with the same thing locally. In consequence, if you have many different routers with different behaviors from one hop to another, it may lead to very interesting troubleshooting sessions. Okay, now, before we try to classify the different load balancing techniques, I will just bring one last basic concept. You understand that network operators will require ECMP when they need to push more traffic than what a single link can accommodate, and also when they need multiple paths for resiliency. But there is one important other use case that I named the Anycast scenario. And it is when the network manager needs to distribute traffic in a deterministic manner to stateful services. Don't worry, I will come back on that in a few minutes. So to categorize the different load balancing techniques, I will use two dimensions, static or dynamic on one axis, local and remote global on the other. That gives us four categories, but in reality the static global makes no sense. So eventually we will sort our options in three groups. First, the local and static. The forwarding decision is based on fixed fields present in the packet header or the payload. You certainly have heard about the term hashing. We'll come back on that very soon. Second category, local and dynamic. Here we will introduce additional real-time parameters to the forwarding decision. For example, we're going to consider how occupied are the interfaces or the buffers. Third type, dynamic and global. It does reuse the same parameters that the second category, but this time it will also add dynamic metrics advertised by the neighbors in real time. To simplify the understanding, I took the liberty of creating an abstracted view of the ingress and egress forwarding ASIC made of different functional blocks. Each packet will go through all of these blocks when it goes through the router. First, we have the parser. Its job is basically to extract specific fields from the packet. Then we have the hashing, where we'll compute a mathematical function based on those fields. Followed then by the lookup phase, where we'll identify the next stops. Then the next stop selection, picking one of the possible exit points for the forwarding. And finally, I added this other abstracting function, the next stop ordering block, who is responsible for sorting the feasible next stops in a more or less consistent manner. This last block is not computed for every packet because it has been pre-computed at the beginning and it will rely on the routing protocols and the interfaces availability. Okay, now let's continue digging a bit deeper and we'll explore these blocks one by one, and I will illustrate it with an MPLS packet. In the parsing phase, the MPLS packet headers are analyzed and we extract certain fields like the source and destination MAC address, the two MPLS labels and their respective EXP fields, the source and destination IP addresses, the DSCP field value, the protocol type, here we see it's going to be TCP, and finally I will pick the source and destination ports. Note that it is just an example, and I picked these fields in a totally arbitrary manner. When I told you earlier that things are very much platform dependent, it's perfectly illustrated in this phase. Indeed, the default set of fields extracted is different from one product to another. But also what you can configure to add and remove elements of the list could be different from one box to another, sometimes from one OS version or another. So when we have all those fields selected, we move on to the hashing phase. It's nothing more than a mathematical operation. Usually it will be a CRC function, a polynomial cyclic redundancy check, taking the various fields we selected in entry and resulting in a fixed size value. Some systems may calculate multiple different hashes for each packet, whether or not they will need to use it in a later phase. Some example that comes to mind is we can use that for the computation of the entropy level. Before we move to the lookup phase, just one word on the next stop object that Junos creates for the forwarding. It's actually a topic that deserves by himself many hours of presentation to be covered decently. So I will just scratch the surface here, listing a couple of examples. So the particular next stop object pointing to a network interface are called Anycast. Sometimes we also refer to them as direct or final. We call aggregate an object dedicated to the members of a link aggregation group. And I will not detail all other types of next stops, like the indirect of composite ones, but I will mention one essential for the load balancing mechanism, the unilist. With a unilist object, you can map a destination network to the different path options. And it's a very powerful construct that contains potentially many other next stops or hierarchies of next stops with multiple levels of indirection. And in the show comments, you will see that represented by these four letters, ULST. Okay, let's get back to our abstracted representation and we'll reach the lookup phase. Here, the destination is resolved via a unilist next stop, itself composed of multiple entries. These entries are sorted in an index table, represented here. We have this first array or structure or matrix, if you want, the index table. The entries of the index table are used to populate another table called PFE distribution. Sometimes we call that Selector Table. Again, I insist I'm taking a lot of shortcuts here and I'm generalizing for the sake of simplicity. Please accept a certain level of abstraction. This selector table is made of buckets, identified by their position, and they contain the index values we presented earlier. The hashing result that we computed also in a previous phase, or at least a modulo of this hash value, is actually a pointer to the address, to the position of a bucket. Now we have all the elements that we need. The hash value points to a bucket in the selector table. This bucket contains an index ID value, That itself could be resolved to an egress interface based on the content of the index table. Now, our PFE knows how to select the egress interface for this particular packet. Let me show you very quickly an illustration on an MX router based on Trio 6. And we have, in this example, 4 paths for a particular destination address. On the top of the output, I can see that I have indeed 4 next hop indexes. And in the bottom part, I see that I have 128 occurrences of each category. The selector table is made of 512 entries, so 128 is indeed a quarter of the available space. That's a typical equal cost multipath case. And to continue with the illustration that I used earlier, the hash key results point to a bucket containing index ID number 3. So let's continue with the categorization of the different load balancing techniques, and we will map them to different use cases. Case number 1, a typical ISP. Here we have thousands of users, themselves generating dozens of streams towards services to or from the internet. Most of these streams are short-lived. So we deal with millions of flows with a lot of variety that will reflect in a lot of entropy from the hashing algorithm perspective. We usually don't need to make specific adjustment to the load balancing technique. Most of the time per flow mode is enough, whether it is default or it does require configuration. I will come back on that in a few minutes. But some specific use cases may require specific solution. For instance, when we have pseudo-wire or GRE traffic between sites, just to name a few. The next scenario is what I referred earlier as Anycast use case. In this other example, we have a farm of servers or appliances delivering a service, and this service requires to maintain stateful tables. For example, it could be a security service like a stateful firewall or even CGNAT. If the service requires more than what can be delivered by one device, we need to scale up and optimize the resource. Also, we want to guarantee a certain level of redundancy, and we have multiple routers facing this farm of server. That means we need a deterministic load balancing mechanism to make sure packets with a certain attribute will be forwarded to the same server, regardless of which router they land on. In the data center world, and even more specifically in the AI, machine learning, HPC environments, we have to address another kind of challenge. Here, the flows are very long-lived and high bandwidth. I mean, close to line rate, 400 gigabits per second or 800, potentially for days. That creates a unique problem, and specific load balancing features have to be developed to address it. Let's dig deeper in these different load balancing techniques, starting by the local static kind. I will not describe this slide point by point because my key message here is that load balancing behavior and configuration will be very different from one platform to another. You heard me repeating that many times, but that's very essential. And I only considered Juniper routers. Imagine what it is in a multi-vendor environment. Let me take a couple of examples to illustrate my point. By default, on your MX routers, you don't have any load balancing enabled. Even if you configure your IGP and BGP for multipath, it's not going to the hardware. The forwarding ASIC will be programmed with just one single path based on the destination address. If you want to activate proper load balancing methods, like the per flow mode, for example, you need to configure a policy and apply it in export to your forwarding table. The default behavior on PTX 10K or 12K is very different. Indeed, without any specific configuration, ECMP will be enabled. It will automatically pick certain fields in the packet or even select some metadata to create the hashing. So by default, on PTX running Juno Civo, per flow mode is activated. Now, another example to illustrate the differences between platforms. And let's get back to the MX. When you configure per flow load balancing, the default list of header fields the system will extract to perform the hashing computation will depend on the ingress interface configuration, while it will always be the same field selection for PTX 10K or 12K. In this example, for an IPv4 packet received on the routed interface, you notice that the MX is not inspecting the L2 fields, while the PTX will pick ether types, source and destination, MAC addresses, potentially VLAN ID if it's configured. On SCX 7000, it's even a different approach, When you enable per-flow load balancing, no fields are selected by default. You have to explicitly list what you want in your hashing. Finally, on QFX, we have two profiles. We consider the L2 header or the L2 payload. And then you can select with more granularity what you want to add or remove for hashing inside this mode. I'm not trying to scare you with all these differences. Many network operators have a perfectly happy life without knowing these details. But if you start to care about load balancing, keep that in mind. Different products, potentially different behaviors. If you are a long-time user of the Juniper products, you may remember the days we used to call it per packet. It was misleading since the rest of the industry called this behavior differently. So we eventually deprecated the CLI in favor of a more self-explanatory per flow. For most players in this industry, per packet means packet spraying, which is something we also support on MX and PTX via the random option in the policy. This feature is needed in certain cases, and I will cover that later. It's actually the methods offering the best possible balanced distribution on the links. But keep in mind that spraying implies packet reordering needed on the receiving side, and some applications or stacks may not like it. Now let's explore a couple of challenges most implementations need to address when they are running the hashing logic. And I use again the same basic topology: one ingress port, 4 ECMP direct next stops. We create the index table and the PFE distribution table, selector table. The hash key of the selected fields results into a pointer to a specific bucket. So the system will pick interface 4 for this particular packet. And now imagine an outage, the interface 3 going down. Remember, it's a different interface than the one that is used by my packet. In such a situation, you would not expect an impact on your flow, since it's a different interface, right? We've now just interface 1, 2, and 4 available for ECMP in the index table. The selector table is reprogrammed with these 3 entries, and to do so, we have to modify a lot of buckets represented in orange here. After the recomputation of the selector table, the bucket my hash key is pointing to now contains index value 2, and therefore the next packet of my flow is now pushed to interface number 2. This transition should not result in packet loss most of the time, but potentially packet may be received out of order for a brief period. Not great, right? And it could get worse, because now imagine my interface number 3 comes back to life after a few minutes. The same process rehappens again, and the bucket entries are reshuffled. My flow is moved again to interface number 4. So twice the pain when interface 3 goes down and when interface 3 comes back to life. The solution for this scenario is called consistent hashing, or sometimes it's referred to as resilient load balancing. Now let's replace the steps described earlier, this time with consistency hashing configured. When interface 3 will go down and entry 3 is removed from the index list, we will modify the selector table differently. Only the buckets previously occupied by index 3 will be repopulated with index 1, 2, and 4 to keep the distribution even. Consequently, all the flows pointing to other buckets are not impacted. And it works fine in both directions. When interface 3 goes back again, the same steps will be followed. In our example, the flow is not impacted. As mentioned several times, it's a very high-level and simplified description of the behavior. In some implementation, we are using smart approaches where we can keep in memory the last selector table to restore it faster if the same interface comes back to life. Also, it's pretty cool, but it's not magic. It comes with some obvious limitations. For instance, if we increase the number of possible next stops, if you had one more server, for example, on your farm, that will naturally trigger a reshuffling of the selector table entry. In this example, we start with 4 ECMP entries and we add 1 extra path. We now have 5 entries in the index table. It will change entirely the content of the selector table too. Also, keep in mind that it is not supported with all routing protocols. You need to pay attention to that. In many implementations, it may be only eBGP. This is the first challenge that can be addressed with consistent hashing. Now let's take a different scenario now with 2 zones, trusted on the left of the firewall, untrusted on the right. The host on the trusted zone sends a TCP packet to a server on the internet, and a state is created in firewall number 4. On the return path, we swap source and destination addresses and ports, and the packet is handled by the router where the load balancing process will be executed again. If the router eventually selects an interface and the packet goes through a different security device, like Firewall 2 in this example, then we have a problem, because Firewall 2 does not have the state information in memory. The packet will be probably dropped unless we use certain other high-level mechanisms. So we need to guarantee a symmetrical behavior. By symmetrical here, I mean a mechanism that guarantees that you can restrain the hashing on certain parameters, like IP source only or IP destination only, and ignore all other parameters. And it requires additional tricks. A different angle of the same problem is illustrated in this example here, where we have multiple routers to reach a farm of servers, delivering a stateful network address translation service. Here again, we need a deterministic, predictable approach to guarantee that packets originated from a certain host will always be handled by the same CGNAT device. The solution is logically named symmetrical load balancing, and it can be implemented in different manners. But in all of them, we need to add the sorting mechanism of our index table. In this example here, the sorting of the index entries is based on IP addresses, not interface naming, not position, but really the value of the IP addresses. It's simple and elegant. It guarantees the indexes will be aligned between the two routers, regardless of the position of the ports. Also, we need to restrict the fields used by the hashing algorithm. Source IP only on one side, destination IP only on the other. And that way we make sure the hash key will point to the same bucket. In certain implementations, we will also need to force the same hash seed value on both routers. By default, we are leveraging the MAC address, the chassis MAC address, that will be obviously different between two routers. So if we force this hash seed value or ignore it for the hash computation, we guarantee the hash key will point to the same position, same bucket on each side. So in terms of support on the Juniper product, the consistent hashing is available on MX series, PTX 10K and 12K, and SCX 7K. So symmetrical load balancing is fully supported on MX series and could be implemented on PTX, but with specific operational restrictions. Very briefly, a few words on a technology named TLB for Traffic Load Balancer, implemented on MX routers. The naming of the feature is not super original, I admit, but the feature itself is pretty neat. It's something that we use in solutions like the CSDS, and invite you to check the JVD here for extensive details on the behavior. But in a nutshell, the feature includes a regular verification of the health of the devices, for instance, an NSRX firewall. In the past, this feature required a dedicated service card in an MX 960, for example, but more recently it has been introduced on modern MX series like the MX 10K and the MX 304. Instead of the service card, that does not exist on this product, the health check job is done by the routing engine itself. Based on the health status, the system will manipulate the selector table. It will program specific addresses and also filter-based forwarding for the return path. And again, you will find the link to the Juniper Validated Design, the JVD, in the description if you are interested in more details. Now, let's move on to the second category of load balancing technologies, the dynamic ones. And it's a requirement that may appear in many situations, not only in data center environment. I will ask you now to imagine a new example where we will have a lot of small bandwidth flows and just a few high bandwidth ones. When performing the index ID selection, the system does not take the bandwidth into consideration, but only fixed parameters extracted from the packet header. Statistically, you can imagine the distribution will be balanced in terms of number of flows per interface. But if you have one large flow, like the one I represented in purple, which is directed to interface ID 4, and it is using more bandwidth than the rest, we create an unbalanced traffic distribution in bits per second and potentially a congestion situation. On the PTX and MX routers, we will use adaptive load balancing to address such a situation. With ALB enabled, the router will monitor multiple KPIs. First, the link utilization. Second, it will count the bytes forwarded for each bucket in the selector table. Based on the link utilization, if an unbalanced situation is detected, the router can take the decision to smartly repopulate the selector table to optimally rebalance the traffic between links. And it can do it every 30 seconds by default. This mechanism relies on a lot of counters in the selector table, and both MX and PTX are very capable platforms in the matter, with 8 million meters or counters available. So we have ALB used in many production networks. In the WAN side, it was initially designed for link aggregation, but the support for ECMP has been extended more recently. And here again, I will suggest you check the documentation to verify the routing protocols supported in this mode. Let's consider a different use case, the DC technologies. In this world, 3-tier or 5-tier cloud topology is the norm, and consequently, every destination is reachable through multiple spines, multiple paths. That means ECMP everywhere. In the HPC and AI/ML environment, it is very common to have very high bandwidth and long-lived flows. These flows show very little entropy, in their packet headers, to distribute them evenly on the multiple links, and we need to find other mechanisms than the typical static hashing formula to optimize the balancing. In QFX series, the solution is based on a hardware component inside the PFE directly, whether it is Tomahawk or Trident. Naturally, Broadcom calls this dynamic load balancing, or DLB. Instead of relying on the packet header fields or payload, the forwarding decision will integrate other parameters collected in real time. The ingress port link utilization and the virtual output queue depth, which is the number of cells stored in the buffer to be transmitted to the egress port. Based on these parameters, it computes a value, the port quality number, that will be used to pick one port or another. And DLB is available with 2 configuration options. First, you can select the per packet mode that we introduced earlier. It will perform a weighted spray load balancing based on the quality of the links. And as we mentioned several times already, when we talk about spraying, it means potentially packet reordering. The second DLB configuration option is called the flowlet mode. It consists in identifying subflows inside the long-lived macro flows. Simply by detecting pauses inside the flow, we can create flowlets. And each flowlet will be treated independently from a load balancing and forwarding perspective. And here again, based on dynamic parameters like the port quality. But pauses can't always be detected inside a long-lived flow, and the link's quality can evolve and lead to an unbalanced situation. And that's why some safety net features have been created, like the reactive load balancing. Basically, it takes the decision to reshuffle the distribution after a certain amount of time, if it was not able to detect a pause long enough to create flowlets. Also, it's good to mention that we can differentiate the flows and assign them a different load balancing treatment. And with selective DLB, we can match just on certain parameters inside the payload. For example, we can just capture RDMA OP code and treat it the way we want. If you remember the categorization of load balancing techniques, we covered the static ones and the local dynamic ones with ALB on MXPTX and DLB on QFX. Now let's talk about the last group, the dynamic global. Indeed, DLB can only measure the link quality locally to the device. But what happens if the congestion happens one level above? For example, between the spine and the destination leaf. The source leaf have no way to know that a particular spine is not in position to optimally forward the traffic they will send to it. That's what GLB, Global Load Balancing, intends to address. Here we have 2 mechanisms at play. One to signal through BGP the next hop topology, and another to multicast the link quality information from the spine to the leaves. Based on this information, now the leaf can decide where is the best path for a flow. And yes, you can mix DLB and GLB on the same device. Again, these innovations are particularly useful in DC environment and will not make much sense in a wide area network design. Before we wrap up this video, I will talk again about packet spraying, and for a simple reason. Many of the elaborated techniques I briefly covered here are used because the endpoints cannot deal with packet reordering. But if we remove that limitation, the use of per packet load balancing will become both the simplest and most efficient approach in terms of link utilization and traffic distribution. I mentioned earlier this feature is supported selectively on MX and PTX, meaning you can decide which flow should be sprayed or not. And more advanced approaches exist on QFX with DLB, but also with functions like WPS, weighted packet spraying. a feature that integrates the knowledge of the topology, the next stop if you want, and permits a smarter distribution of the spraying. Okay, for example, in this illustration, if the spine to destination leaf connectivity is reduced for a specific spine, the source leaf will know it cannot send more traffic that the second leg can handle. Also, new techniques like UET, Ultra Ethernet Transport, are natively designed for RDMA transport and packet reordering. And they also integrate entropy fields when they are not using a UDP header. The good news is that more and more smart NICs are capable of packet reordering. When it will become the norm, probably we'll forget about all these techniques to only use the different flavors of packet spraying. Finally, many static pinning approaches based on Q-pair values have been developed, and I will link a couple of good videos and presentations on the matter if you are interested. Okay, let's close it now. I've probably taken too much of your time already, and I doubt anyone will go that far in the video. You can tell me in the comments if you happen to see that part. We'll recognize the braves, or the crazy ones. Let me summarize what we said in this video. Per-flow load balancing is probably enough in a WAN environment, even if some tweaking is always possible. Pay attention at your router specificities. Default configuration can be different from one product to another. Consistent load balancing can help reducing the impact of links flapping, for example. No reason to not leveraging it when it's possible. When your end device can deal with packet reordering, per-packet load balancing or spraying will give you the best results. If you expect a predictable behavior, symmetrical load balancing is the way to go. MX is clearly leading in this category, but under certain circumstances, it's possible to recreate the environment to make it work with other routers like PTX. For AI/ML workloads, if you are not using packet spraying, you can introduce additional dynamic parameters in the next stop selection process. That's what ALB in certain manner, but mostly DLB and GLB will do for you on the QFX side. And yes, again, packet spraying is certainly the way we will approach load balancing in the future, when all NICs will support packet reordering. Finally, I will not pretend it's a simple topic. It will be absurd to claim the contrary. The confusion I can see discussing with customers convinced me it is not a trivial topic. But I hope this video was a step in the right direction. I've been Nicolas Février, and I will see you in the next one, probably not talking about those products. See you soon, guys.